In this video I'm going to introduce you to a type of discrete probability distribution called the binomial distribution, which is used when we're looking at probabilities of events that can either have a success or a failure. So if we're flipping a coin, for example, and we're looking at how many heads we get, that would be the success, and the failure would be flipping it and getting a tails. And so we can use this distribution to calculate probabilities where we're looking at, say, getting a certain number of successes out of a certain number of trials, which just means if we're looking at the coin, say getting 10 heads out of 50 flips of the coin, for example. So we're going to start off with a question that I think introduces this idea quite nicely. Then we're going to look at a generic formula to help us calculate these probabilities, and then we're going to finish with a question. So if this video is useful, please do like and subscribe. Okay, so to introduce us to the binomial distribution, as well as the formula for binomial probabilities, we're going to look at the following question. So it says I flip a bias coin 3 times. Given the probability I flip it and get heads is 0.6, and the probability I flip it and get tails is 0.4, we're asked to find the following probabilities. So let's start off with A, which is the probability we get 0 heads. Well, that's pretty straightforward, because to get 0 heads when we flip a coin 3 times, the only way that's going to happen is if I flip it and get tails all 3 trials, or all 3 times. And so we could say the probability of getting 0 heads is going to be equal to, well, the probability of getting tails multiplied by, again, the probability of getting tails multiplied again by the probability of getting tails. So it's basically just doing 0.4 cubed, and then that gives us 0.064 as our probability. Part B, though, that's a bit different, and you could use a probability tree if you wanted, but let's think about it a different way. Let's think, how many ways could I get 1 head in 3 flips of a coin? Well, I could flip it and get heads straight away, and because I want exactly 1 heads, that means I have to get tails the next 2 times. Or we could get tails first, then heads, then tails again. Or I could get tails, tails, and then heads. So these are the different outcomes we could have. So let's calculate the probability. So the probability I get exactly 1 head is going to be the probability I get heads on the first trial, which is 0.6, multiplied by the probability we get tails, multiplied by the probability we get tails again. Or we could get tails first, then we could get heads, then we could get tails again. Or finally, we could get tails, then we could get tails, and then we could get the head on the final go. Let's now rewrite this, and you'll see why I'm doing this in a second. So we have the probability we get heads, which is 0.6, times the probability we get tails twice, so I could write it as 0.4 squared. And hopefully you'll notice this is exactly the same as all the other times, because we're basically just seeing the different ways we can get heads once, tails twice. So I could write it as 0.6 times 0.4 squared plus 0.6 times 0.4 squared plus 0.6 times 0.4 squared. And again, we could write this differently. We could say, well, this is exactly the same as doing 3 lots of it. So 3 lots of 0.6 times 0.4 squared. Okay, and to make it even clearer what I'm now going to say, I'm going to write it like this: 3 multiplied by 0.6 times by 0.4 squared. Okay, so why have I chosen to write it like this? Well, you'll see why, because it will link nicely to the binomial distribution. So the first part, this 3, where is that coming from? Well, that's because we asked how many different ways are there to arrange that 1 head that we want and the 2 tails that we're going to get. Well, we found out there were 3. And if you know about the binomial coefficient, we could have calculated this 3 by doing 3 choose 1. Because we're looking at how many times can I arrange, or how many different ways can I arrange 1 head and 2 tails. So 3 choose 1. I'm then multiplying it by what we would call the probability of success. So a success would be getting the heads, because that's what I want. So the probability of a success, well, the probability of getting heads was 0.6. So that's where this 0.6 is coming from. And how many times did I want to get that success? Well, I wanted it once. And then finally, I multiplied it by what we would call the probability of failure, which was getting the tails, because that wouldn't be what we want. We don't want to get tails, we wanted to get the 1 heads. So the probability of failure was 1 minus the probability of succeeding, or 0.4. And how many times did we need to get that failure? Well, it was twice. So hopefully you can kind of see where this has come from. And this is kind of the basis for our binomial distribution, and we're going to use this to help us answer part C pretty quickly. Hopefully this will be clear how this is going to work. So now I want to know, what is the probability we flip the coin and get heads twice? Well, let's think. We're now looking at how many ways we can arrange 2 heads and 1 tail. So I'm doing 3 choose 2, okay, because heads is the success. So 3 choose 2 multiplied by the probability of success, and I want that twice, so squared, multiplied by the probability of failure, which is 0.4. So let me now calculate this using my calculator, and I get 0.432. So you can see that's a lot quicker than doing what we did above, or drawing out a probability tree and multiplying along the branches and summing them at the end. So this is a quick way that we can calculate probabilities, and this is our binomial distribution. But to be able to use this, we have some conditions that we need to meet, and they are as following. We have criteria. So for the binomial distribution to work, or for it to be a binomial distribution, we have to have a fixed number of trials. And in the above example, there was a fixed number of trials because we had 3. We were flipping the coin 3 times. All of these different trials have to be independent, which again they were. Flipping the coin the first time didn't have any, it didn't change the second flip of the coin because they're all independent. The probability of a success, which we'll call P, has to be the same in every trial. And again, it was in the above example because the probability of getting the success of the heads was 0.6 every time. And finally, each trial is either going to be a success or a failure. So in the above case, it was either getting a heads and succeeding, or not getting the heads and failing. So let's now look at a generic formula that we can use. So given our random variable x belongs to a binomial distribution, that's how we would write that, where we're having n trials and the probability of success is p, then the probability, our random variable, is equal to x, where x is like the number of successes if you like, is equal to n choose x multiplied by the probability of success to the power of x multiplied by 1 minus the probability of success to the power of n minus x. And if you look back at the above example, you'll see that's basically what we were doing. So let's bring this formula down and look at a final example. So here I'm rolling a fair 6-sided dice 50 times, and I need to find the probability that I roll 26 4s. So let's first write this out. So I have my random variable x belonging to a binomial distribution. There's going to be 50 trials because I'm rolling the dice 50 times. And the probability of success, well, it's a success if I roll a 4, so that's 1 over 6. So we want to know the probability that I have 26 successes, so x is equal to 26. And so that's going to be equal to, well, 50 choose 26 multiplied by 1 over 6 to the power of how many successes? Well, 26, multiplied by 5 over 6, which is 1 minus the probability of success, to the power of n minus x, which is 24. So let me now put this all into my calculator, and I'll tell you the probability that when we're rolling a fair dice 50 times, we get 26 4s. And this is kind of a silly question really because it's so unlikely, but we get the probability it's 8.9 times 10 to the power of negative 9. So it's very, very, very unlikely, which if you think about it, it kind of makes sense. The probability of getting over half of your rolls of a dice being the same when you're rolling it 50 times, it's quite unlikely. So hopefully this video was useful. If it was, please do like and subscribe, and go over to my channel where I have tons of other maths tutorials. Thanks for watching.